Good day, folks. Today we will be practicing logical binary shifts. There are two forms, you already know it, a logical shift left and logical shift right, shortly known as LSL and LSR. Okay, as an example, I have done some homework on an exemplary value of 75 as a denary value whose binary equivalent is written and has been filled into the boxes. Now, let us perform both of the shift one by one. We'll start with the left binary shift. Okay, so to start with, as I have mentioned with the arrows, that most of the left hand side one digit or bit on the most left hand side, or also known as MSB, most significant bit, will be lost it away because it is on the most left corner. And when it will be shifted on the left side, there is no space except to put it in the trash bin. Okay, so this bit will be wasted away. For now it is 0. It won't be any meaningful to be wasted away, but when it is 1, we might lose some importance. We'll see it in the second shift. Okay, so this one will be written in here, this 0 in here. So I'll start writing as I have already mentioned through arrows. So we got 1 0 1, sorry, 0 1 0 1 1. So as you have seen that on the left hand side we have lost a 0, and so on the right hand side during the left binary shift we have come up with a hole, and to fill the hole we can only fill them with the zeros, none other than the zero. So remember it, we always have to fill the holes with the zeros. Okay, so this is the one logical left shift or one logical shift left. Okay, because we have shifted each digit one place to the left. So we'll now compute its denary value, because it's the second category of question that comes in the paper, that what effect did this shift had on the logical boundary value. So we started with 75. We started with 75. Okay, and now we'll compute its 2 4 8 16 32 64 128. Okay, 128 plus 16, 4 here, 1 carry here, 2 4, and it's 144. Okay, 144 then plus 4, how much? 148, I guess. Then plus 2, it's 150. Okay, so the new binary value has the value of 150. Or I'll write it here. This is the binary value for 150. Okay, now right on this spot we'll try to have a link between 75. Let's do 75 into 2. 5 twos are 10, 7 twos are 1 carry 14, and 1 carry added 50, 150. So we have seen the effect of the one logical left shift on the original 75 binary value as it has been multiplied with the 2. Okay, I'll do one more binary shift, and for that I need to have that blank. Can I copy? Okay, try to copy them. Fine, paste. Luckily we have that copied. Okay, again I'll copy it, paste. All right, We'll perform another shift, and by that shift we'll have this one be wasted away. Okay, this 0 will come here, this here, this here, this here, this here, here, and obviously this is the legit value now for the next binary shift. So we have come up with 0 0 1 0 1 1 0 0 0 1 0 1 1 0, and now we have again a hole, and we'll fill it with 0 again. Okay, so now let us compute the value. New value 1 2, this is 4 8 16 32. Okay, I don't think so it will be 32 plus a is 40 and it's 44, so the new value is 44. Luckily, we have seen that one logical left shift on 75 was perfectly fine, but when we shifted it again, or we can say we shifted 75 two places to the left in this step, two places to the left, because this is a second shift on the 75. We did it step by step. Okay, so the second shift on the 75 has produced a wrong value. So the effect of this shift, we can write it as the value is wrong, because as written in the book, the author says there is a limit to the binary shift. It's looking like a multiply. We'll write it as cross. Okay, it's wrong. There is a limit to the binary shift that can be applied to 8-bit binary number or 9-bit binary number. Or to make the shift correct, we have to increase the number of bits. If it could have been 9 bits container, the answer could have been perfectly fine. What happened actually is, if you notice, we had this most significant one which had the value of 128, which has been lost into the trash. Okay, so we have lost our most significant one bit having the value 128. So we only came out, we have only left with 32 plus a plus 4. That cannot make up the twice of 150, which is 300. Oh, okay, I can even show you the other way. If it could have been 300, if you notice, an 8-bit register or 8-bit container cannot contain a value greater than 255. Okay, that means if we turn all the ones on in a 8-bit register or in a 8-bit pi, we only come up with a 255 at max value in a 8-bit byte. Okay, so the answer could have been 150 into 2 300, but 300 cannot be fit into, so we have performed a correct logical left shift, but the answer is incorrect. So the effect of this shift, you will write it as the effect of this logical shift is incorrect. Okay, so I will now sum this up as okay, oh fine, luckily. And now I'll sum this as up that the logical left shift has an effect of multiply by 2 each time. Each time multiply by 2 with the original number. So we have performed one logical left shift would be 2 multiply by 2. Then and again logical left shift will have an effect of multiply by 2. Okay, again multiply by 2, so we can also write it as 2, then 2 into 2, this will be 4, and then 4 twos are 8. Or we can write it as each binary shift multiply the original number by 2 raised to power 0, which will be 2 sorry, 0, there is no 0 place. First logical shift does the multiplication with 2. Second logical shift does the multiplication with 4. Third logical shift will do the multiplication with 2 raised to power 3, which is 8. It means If it could had been 300, then we'll again shift the logical shift the number to the left. Then it will have an effect of 300 multiplied by 2. So multiply by 2 in here, multiply by 2 in here, then multiply by 2 in here. Okay, this is a fact that answer is coming incorrect, but the effect of the shield will remain the same. 2 into 2, this becomes 4. Overall, totaling or simplifying, and 4 into 2 will become 8 actually. So, okay, so we are performing them by step. So it's multiply by 2, then multiply by 2, then multiply by 2. So on the third step, if you multiply each two together, will come up with the 2, 4, 8, 16, 34. Okay, so it is always in the form of 2 raised to power 1, 2 raised to power 2, second logical shift. Third logical shift will have a factor of 2 raised to power 3 or 2 raised to power 4. I believe I can put more light onto it. In another way, if we multiply, that simplifies to 2, that simplifies to 4, 8, 16. Okay, so we'll do what? The first logical left shift on 75 as an example. On 75 as an example, we'll have an effect of 75 multiplied by 2. Then second logical shift will have an effect of 75 multiplied by overall 4. Okay, overall effect will be 4, but on a single side it will be have an effect of multiply by 2 again. Okay, or we can also, because 70 Now I'll show this step with an example on 75. Let's suppose we have performed the left logical shift on 75 and it gave us effect of 75 into 2 multiplied by it will give us 150. Then the second left shift will have an effect of 150, which is this one, multiplied by 2 is equal to 300. It could had given us if we had 9 bits. So can I say that the original number has been, if we multiply by 75 by 4, that's also is equal to 300. Why? Because we have performed the shift by steps. We have performed the shifts by steps. Multiply by 2, then multiply by 2. Okay, so overall it's 4. So I can say the direct two logical left shift on 75 could had an effect of 2 raised to power 4, which is 4, which is also can be proven as 75 into 4 is equal to 300. Okay, you can understand it better by an example from the past paper I have down below. Now we'll move towards performing the right shift. Okay, another way to remember that whether the left shift multiplies or divides. So if you could see, shifting the number on the left hand side, the powers of the bits or the weightages of the bits are increasing on the left hand side or towards the left hand side. After 128 we'll have 256, then 512. Okay, so if the digits are shifting towards the left, or even digits, what matters to us is the number of one bits in a number. If we shift one in here to here, then it becomes from 256 to 512. Okay, as in this example, this one on the weighted 64 had become in here 128. Okay, so on the left hand side, because our weightages of the bits are increasing, that's why we have the effect of multiplication with the 2 each time. Let's suppose if an examiner asks you to perform a shift of 4, shift of 4 on left, then we can say the original number will have an effect of the original number, whatever it is, will have an effect of 2 raised to power 4, which is original number. We don't know what's the original number. Let's say it is a question mark, but that will be having an effect of 2 raised to power 4, which boils down to, simplifies to 16. Okay, which is actually not possible in a 8-bit register. But even though the answer is incorrect, but we have performed the shift perfectly well. The effect of the shift will remain correct, to raise to power 1, 2, 4, 8, 16. This will apply. Okay, now let me clear the board. Fine. We can now erase them. Okay. On the right hand side, the opposite is the solution. If we had an effect of multiplication, um, multiplication effect. Okay, so we can say we will have the opposite of it, which is the opposite of multiplication is division by 2 each time we perform a shift. So we'll perform the shift on the same 75, so it should half it. The half of 75 won't be a perfect even number, but we'll see what will happen. Okay, we'll start filling the numbers. So we'll start filling from this 0. Okay, we'll start filling from this 0, and the number becomes 0 1 0 0 1 0 1. Okay, so this one has been wasted away. If you could see, we had 2 1, but we have come up with a single one on the, so one bit on the right hand side has been wasted into the trash, so we came up with a hole on the left hand side. Okay, so we should fill that hole with the 0, even if it is left or even if it is the right shift. Holes are always filled with the 0 in the shifts. Okay, so we'll now compute the equivalent denary value we have come up with, just like we did it in this step. Okay, we came up with 1 2 4 8 16 32. 1 2 4 8 16 32. Okay, 32 plus 4 is 36, then 37. Okay, so this is 37. Okay, if we could had a calculator with us, if we do 75 divided by 2, we come up with 37.5. Okay, 37.5. 37.5 we have come up with. So we'll simply discard the 0.5 factor, because it's always the integer division or integer multiplication. Integer division it is. Okay, so in integer, 0.5 cannot fit into, because that's a category of real numbers. Integer can only have the whole numbers, so we'll only take 37. Okay, so the effect of original number, sorry, I'll use the red marker. Effect of the right shift on the original number 75 is as it has been halved. So we'll put a multiplication sign here, and we'll do a division sign here. Okay, so if we perform another left shift, I believe I have that in, no, okay, we can put it in here, and fish, we, uh, yeah, this one. Hmm. So I have ready a new container. So performing the right shift now again, we'll start it from the right hand side, shifting the, so the rightmost one or the least significant will be in trash, then this, then this, then this, this, this. Okay, so we'll start with, always remember, right hand side starts from the right hand side, left hand side starts with the left hand side. Okay, so we will fill it with a 0, sorry, I had to use orange. Okay, 0 1 0 0 1 0 0 0 1 0 0 0 1 0 0 1 0 0. Again we have come up with a whole, we'll fill it with 0. Okay, let us now compute the number. The number we have come up with, 2 4 8 16. 16 plus 2 is 18. We'll see 37 divided by 2 is 18. Luckily we have a correct division. Okay, so the factor of shift has, on the original number is, as it has half the number again, so as it has half the number twice, so we can say it has divided the original number 75, divided the original number by 4, and as I have mentioned, as we have done it in steps, 75 by 2 will come up with something, yeah, it was 37. Then again 75 by 2, we came up with 18. As we have divided the original number 2 times with 2, we can say it, we have divided the original number by 4. Okay, so this 2 and this 2 will sum up to make it 4. I'll prove you guys with the calculator. 75 divided by 4 is, it should be 18. 75 divided by 4 is 18. Okay, so we'll just simply discard the decimal part, and it's 18. Okay, so the effect of shift on the right hand side is, as it has been multiplied, divided each time by 2. Okay, so the same scenario, but division on the right hand side. It has already taken too long. Now we'll move towards the past paper. An 8-bit NIB binary register contains the value, this one, convert the binary value to denary. So we'll 1, 2, 4, 8, 16, 32. 16 plus 10 is, sorry, 32 plus 10 is 42, 42 plus 6 is 48, 48 plus 4 is 52. I'll again confirm it from the calculator. 32 plus 16 plus 4 is 52. Okay, so the number is 52. You just have to write this way. Okay, the contents of the register shifted one place to the right. Shifted one place to the right, remember, will start shifting from the right hand side. So this will be wasted away out of the league, so we'll start filling from here. Okay, so we'll do what? 0 1 0 1 1 0 0 0 1 0 1 1 0 0. Okay, so we came up with the whole on the left hand side by doing the right shift. Okay, here it was right shift, fine. I'll show with the arrows, sorry, this, 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 and this one will be discarded, then this one, this one, this one, so we came up with a whole. Okay, clearing everything up. Okay, so now we'll again compute the number 2 4 8 16. 16 plus 4 is 20, 24, then 26, it is 26. The original number was 52. 52 divided, if we divide 50 by 2, we come up with a 25. So 52 divided by 2 should be 26. 26 multiplied by 2 is, we can do the opposite now. 26 multiplied by 2 is 6 2s are 12, 2 here, 1 carry, 2 2s are 4, and 5, 52. Perfectly well, we have an effect of exact, I'm sorry, what a bad arrow. Yeah, division by 2, because we have shifted one place into the state. The effect of this shift on the denary value, we'll write it as the original number has been halved or divided by 2. Okay, this is the keyword, this is the keyword, this is the keyword. You should be writing divided by 2 instead of halved. Okay, if you had to choose between any of these two. Okay, so do we have another 4 places to the left? I had, okay, sorry. Luckily, I had shown you one shift, but if we could had seen the contents of the register shown at the start of question 4, shifted 2 places to the left now. Okay, the contents of the register shifted 1 place to the right would give the result this one. So its answer is 2 4 8 16. Okay, luckily I have shown you we should write 26 in here. Okay, I've done a mistake, but that mistake has proven to be helpful. So the effect of this is to be divided by 2. Okay, this effect belongs to this shift, so I'll remove this one as he has already given us the 1 bit shift to the right. Okay, the content, this is the actual question, this is the actual question. The contents of the register shown at the start of question 4 are shifted 2 places to the left. Okay, Star or question 4. This is the question 4 and this is the start. Two places to the left. So I have cleared everything up and the start of question 4 is here as mentioned. So we have to perform two places to the left. Okay, two places to the left means we'll start from the left hand side and two digits will be wasted away. We have to start from the third one. Okay, this one, then this one, this one, this one, this one, sorry, this one. You have to be extra vigilant. We have 1 1 0 1 0 1 1 0 1 0. The holes on the right hand side because we have performed the left shift. So we have come up with the number 1 2 4 8 16 32 64 128. 128 plus 64 is 96, I believe. Yeah, 96 plus 4 is 100. 102, 102, then I guess it's 112. Let us confirm it from the calculator. 128 plus 64, it's sorry. Oh, there was 64 plus 32 was 98, 96. Okay. See, 64 plus 32 is 96. Okay. It's 128 instead of 64 and 32. 128 plus 64 plus 16, it's 208. This is 208. And this was 50. 2, so I can write it as, because as I know two places to the left could had an effect of multiplication with 4 in steps. It could have been 52 multiplied by 2, then again multiply by 2, so it sums up to 52 multiplied by 4. It should produce what? We'll see. 4 into 2, 8. 5 fours are 20. 208. Say the effect of the original number. The original number has been, sorry, multiplied is the keyword, half of the keyword, by 4, or 2 raised to power 2. 2 to prove the two shifts, and it has an effect of 2 raised to power. So 2 raised to power is again 4. So I believe it should be very helpful in understanding the topic right from the start. Sorry, it has been too long. Okay, bye bye.